Hi, the SAP-1 base computer has a considerable amount of registers. In this video, I will show you how a register works inside of multimedia logic, and then I will provide a quick overlook of all registers and pseudo-registers inside of this computer. Now, what you're seeing here is the simulation of a simple 2-byte register as it's just wired in. And we are only using the two least significant bits to let you know how it works. We also have a tri-state buffer at the bottom, which we are going to use so as to emulate the fact that we are outputting several registers into a bus. Right, so by seeing the way we wire the address, we can only have access to two possible register slots, which means it is a 2-byte register. And of course, we are only using the two least significant bits of each byte as the data for this demonstration. Now, most registers, of course, are uninitialized. So what we are going to do quickly is set up this address. We're going to call it address 0 with this value. It is 0, 0. You can see that by pushing the right button, nothing happens. It is until after we release it that on the falling edge, the register will take the value and put it in memory. So as soon as I let go, you can see that it's initialized with a 0, 0. Same happens for the next address. Address 1, it's still uninitialized. So once again, I press the button, and by choosing this bit as 0, I'm going to ensure that on the falling edge, the, the second byte that I have in this register, of course related to address 1, is going to be initialized as 0, 0. Now let's make something more useful. Well, you see, of course, it's not just writing zeros in the register. I can, of course, say that I want and put it in. So, for example, we are going to put the value 1, 0, which is upper bit 1 and lower bit 0, into address 0. The way we do so is, of course, by setting address, the second least significant bit, the upper bit, as a 1, and the least significant bit, the lower one, as a 0. Once again, I push the button, I let it go, and now it's set up. And you can see that by going into address 1, the second byte that I have available for in this setup, it's still initialized as 0, 0. So we're going to set it in a different way. We're going to set it as 0, 1. The high bit will be a 0, and the low one will be a 1. Once again, I push it, and as soon as I let go on the falling edge, it's going to set up as a 0, 1, as it just required. So I can play with these inputs, and you can see it's not changing the output since the 2 bytes are already set. And I can go to address 0, see what I initialized then, and I go to this one, and so forth. Now, if I wish, I could make it a 4 byte, an 8 byte, or a 16 byte register by applying all this. As I said at the beginning, we can actually have a 64K register, 8-bit register in multimedia logic. But for simplicity's sake, we are not going to bother ourselves with such a large computer. You're going to see most registers are 1-byte registers, which means I don't even bother put anything in the address register. And in some of them, I actually use the addresses. In most cases, only 16, but for microcode, it's going to be a little bit more. Now, just before going back to the computer, we're going to talk about the tri-state buffer. It is not actually needed in this computer simulation since we are using a multiplexer at the end so as to connect inputs and outputs. But every time you see it, you are reminded, and that's the intention of putting it, that if you are to do this in a real 8-bit bus without these multiplexers, you are to use tri-state buffers so as to prevent data being input from several registers and causing data conflict or maybe, of course, damage to the registers themselves. A tri-state buffer works like this. You have an input, which is, of course, the data that you want to put into the bus if you want to, and you have an enable bit. Whatever you're doing here, if the enable bit is not set, it's not going to go outside. In the case of this simulation, multimedia logic doesn't know what to put in this LED, so it leaves it in an unknown state. But as soon as I set the enable bit to 1, This little bit is going to be output into the bus or whatever. They can set it up right now. So it's kind of an AND gate, except that if the enable is off, it'll be unknown. Right, so going back to SAP-1, we're going to take a brief overlook of all registers that we have in here. We of course have the instruction register and some microcode registers. The microcode is programmed by itself. Well, it's not actually programmed by itself, it's what we program before wiring all the computer. So we don't write to it. You can see that we only have the address lines, and from that we run microcode through every possible state that we want our computer to have. Now, the instruction register uh, is the first register in the simulation, and there's a small bug. It requires me to set the address as 0 so that it actually works, even though it's supposed to work just fine if it's unconnected. So this register is a 1 byte register, and I get to write data to it. Of course, whenever I get an instruction and I wish to decode it, the fetch cycle, well, of course, I get it into this register, and from that I run the microcode registers. The A and B registers are quite simple. They are 1 byte registers. You can see that there is no address set up, so only 1 byte in, 1 byte out. And the A register can actually output data into the bus. So you have A0, different from register B. This is just something that I decided to make for this computer. But if you want to modify it yourself so as to have B register outputting stuff into the bus, if you wish to, you can do it. Now the ALU is a pseudo register, which means that the ALU actually doesn't use a register box as I did explain at the beginning. It is just the sum of all data that we have in both A and B registers. And it can be output into the bus. That's why I have this line of tri-state buffers, but there's not much aside it. You can see that we also have a couple of flip-flops so as to use the flags in our computer. Both carry and 0, they can be provided directly through the computer. And you also have the option to subtract numbers. Now, the ALU will always add these numbers, A and B, unless the subtract enable is high. Whenever it's high, which of course happens in a subtract instruction, it'll then subtract B from A. But in all other cases, what you're gonna see in this here register will be A plus B. Next, we have the memory address and of course the RAM register. The memory address register is a 1 byte register. You can see there are no address lines pulled through it. That means that the address we are using is 0. Now the RAM register is a 16-byte register. You can see it here. We have 4 address lines pulled in. And the reason why we have 4 lines is, of course, we have 4 instructions. Now, most registers are uninitialized, but I decided to initialize them by using this text file, mem1. And you can see that mem1 is just, for most of the registers, of course, a single byte of data, which is always 0. In the case of the RAM register, I actually want to have the program right away. I don't want to set it up like Benito does when he plugs his computer on. So I have this register, and in here I have all computer, well, both the instructions and data that I wish to start the program with. So it's 16 bytes. I get to write it outside of multimedia logic, so it doesn't get erased every time I turn the computer on. And that way I get to program and save programs whenever I wish to run them. Now we also have a program counter register, and this register is a 1 byte register with a feedback function. You can see the ALU right here. We are adding 1 to the program register every time, and we can decide what to do with it. We can either jump, which is to put some value into this register, or we can go to the next instruction, which is basically putting the result, this sum, in here. And of course, I also detect an overflow when the bit related to this number being greater than f is active high, and that way I'm able to reset the counter and put it at 0 with this AND gate shown in here. Now then we have the display register, once again a 1 byte register, and there's some ALU logic inside it. Don't worry, I won't talk about it for now. And The actual last register is not a register by itself, it's a pseudo register. We have this here counter, which starts counting up every time this clock transitions from low to high. And of course, when I reach number 6, which I evaluate by using this AND gate, it resets back to 0. So this is a counter that goes from 0 to 5, and when it goes to 6, it resets back to 0 right immediately. So that's it. That's all the registers we have. Of course, we're going to talk at the boss at the end of this series, but hopefully you're able to understand how this computer works a little bit more. And I'll see you in the next video.